So today we have with us pleasure to have John Hatcliff. He's distinguished professor at Kansas State University. Been working in the area of formal methods, verification, program analysis, and more recently applying many of these formal methods in the cyber-physical domain, specifically related to health applications. So he's going to talk to us about the work that he's been doing on medical device application platforms in terms of a lot of dealing with the certification challenges. So please go ahead, John.
All right. Thank you. Yeah.
One quick question before you start. Some of this is related to the work you're doing as part of the FDA Scholar and Resident,
Right.
as well as your
yes. And I will try to give you in 2 minutes a roadmap because I was asked to sort of share how the different funding agencies and programs have enabled this research. So this is really a rather broad collaborative effort with a number of people. The paper that is reports on sort of the big picture of this work is given at the URL at the top, and it happened to have these authors on it, but there's a much broader group of people that we're collaborating with. And the problem that we're trying to solve is really considering the idea of how you can enable systems of systems research in the context of devices. So my computer is now frozen. Oh, here we go.
Hey, Ronnie, is there any chance we could move the mic just a little closer to John?
John, you can microphone.
Right. Hello? Can you hear me now?
Yeah, it's much better. Yeah, thanks.
Okay, great. All right, so when I'm trying to explain what we're doing to people that really don't have an understanding of what goes on in the modern caregiving environment, I show them this picture and explain, well, I come from a systems engineering background, and even if you look at this caregiving context, you'll see a number of components that you're familiar with. So, for example, you might see various sensors, like this pulse oximeter that's clipped to a patient's finger. You have various actuators associated with the ventilation of the patient and infusion of various types of drugs. You have displays that are showing various sensor readings. You have the clinicians operating on information systems in the context. And you also have, for example, situations where the clinicians aren't just doing their job any way they want. There's actually clinical protocols that they're following. And if you go on the web and Google clinical protocols, you'll come across large organizations that exist just to publish little diagrams like this that are basically flow charts of algorithms that humans follow when they're providing care. Of course, there's also the patient here, and the overarching concerns are the safety of the patient as well as the operators, but also the security of the patient's information. And so if you consider this type of context, what we really have is a system of systems. But unfortunately, in the caregiving space today, we don't have the ability to bring these disparate systems together and coordinate their activities and apply really strong system engineering principles to them. And so that's really the theme of our research, is integrating these different types of systems on a safety-critical platform, and then coming up with ways that we can not only provide algorithms that coordinate the caregiving, but also provide ways of ensuring the safety and security of the integrated system. On the following slide, what I have here is kind of a history of some of this work. I'm noticing there's a couple lines on the bottom of the screen that are chopped off, but I don't think that's going to make a big difference. So the interesting thing about our work is, in terms of the people sitting in this room, we started working on technology for integration and model-driven development that's actually inspired by the Boeing Goldstroke project on the DARPA Pieces project, which David Corman played a large role in. And on that project, we developed a collection of tools for model-driven development of distributed systems following the Goldstroke product line methodology. And Paul Jones happened to attend one of the meetings where we were presenting this work, and he said, is there any way that you could apply that to medical device integration? So in about 2008, Paul helped us get some seed money through the NSF FDA Scholar in Residence program. That was about $50K, and with it we built our first prototype called the Medical Device Coordination Network. Now, it's interesting to note that this first prototype was built as a class project involving a graduate student and an undergraduate student. And so from that sort of blend of graduate and undergraduate research as part of a class project, we were able to build out using a number of different forms of subsequent funding, which I'm going to briefly run through right now. So after we made this initial prototype, we were very pleased to receive in 2009 from the Cyber Physics program a grant that went with UPenn, and that allowed us to develop our prototype simulated devices and so forth. We received an REU supplement for that to work on the security features of the system, and that's going to be important in just a second. In 2012, we proposed a broadening of the effort to include a hardened platform, a standards-based model-driven development using the AADL architecture definition language, partitioning middleware, also use of DDS, if you're familiar with that messaging standard, and integrated security. Now, along that time, we had a new faculty member join who was able to take this work that we had done from a security prototype, and he was able to receive an NSF SATC award in 2012 for $450K, which further built out the security features, and then a broadening of that effort as part of his career award in 2013. So the main message here is, from a little bit of seed money and maybe some insight from Paul Jones, we were able to do a strong transitioning of technology that was really originally targeted to the avionics space and bring it over and start addressing these challenges in the healthcare space. Along the way, what was interesting is, these grants really focus on technology development. They don't necessarily focus on explaining how the technologies get applied in the certification context. And so what's been extremely valuable for us is to be able to work directly with FDA engineers as part of the Scholar in Residence program. And we've been able to say, well, what would it mean to use the model-driven development like AADL in the certified medical space? How can we do things like model-based hazard analysis? How can we define formal interface specification languages that capture the type of behaviors, including timing information, quality of service, and so forth, and have those be a part of the artifacts that are considered in a regulatory submission? There's also a number of other things that we've done, building out things like requirements, methodologies, use cases, architectural models, and so forth, and safety cases in this context that's been enabled by this FDA Scholar in Residence money. Along the way, we were fortunate to be able to collaborate with Dr. Julian Goldman, who received a very large NIH NIV grant for around $10 million, and we contribute to that in terms of being able to transition the architecture certification and security elements into a clinical space to experiment with those in that context. So just a brief overview of the impact of some of this work, which I'm quite excited about in terms of the certification space. I'll give more details about this as we go through the talk. But the main point here is that due to the efforts on this project, I am now a co-chair of the architecture work group on an emerging standard, the AAMI UL 2800 standard, which focuses on medical device interoperability, safety, and security. I'll be talking quite a bit more about that later on. And Dr. Vasserman from Kansas State, because of his involvement in the security work here in the MDCF, is the chair of the security task group within that committee. Some of the work that we've done on integrating AADL in the medical space has led us to develop advances in the risk management and behavioral interface specifications that are also now being rolled into the AADL standard. And our Scholar in Residence that's been funded by this program has contributed quite a bit to pieces of the standard, and he serves on that standard committee. We've also been able to come up with a number of interesting collaborators and push this work forward in the context of both deployed clinical systems and safety certification space, and primarily I'd like to highlight the work that we're doing with Underwriters Laboratory as part of the development of this standard, but also different risk management techniques. And finally, but not last, in terms of importance, we've been able to collaborate with folks like Paul Jones and Sandy Weininger at the FDA to really develop philosophy and guidance for these types of systems that I'm going to be talking about. So that's kind of a broad overview of the topic, and then sort of how the different agencies have been able to come together and contribute funding for this through their different programs. I should also mention that a lot of the infrastructure that we're building on here was actually developed under an Air Force AFOSR grant that we've been able to take advantage of when producing a lot of the tooling for this. So what I want to do in this talk is to give you an idea of what's the motivation for introducing notions of systems in the medical space, and what are the main technology components that we're applying, specifically the concept of a medical application platform. We'll talk about some distinguishing characteristics of MAPS, what we're doing in terms of architectural standards, and then what we're doing in the safety standard space with the AAMI UL 2800 standard. So, well, what's the baseline for all of this? Well, if you're familiar with FDA and medical system regulations, integrated systems these days really start off in terms of what are called medical device data systems. So these are integrated systems where you have devices and they may be streaming their data, but the data streaming is one way to heads-up displays that you might see in a clinician's workstation in a hospital room, or to the electronic health record. And so current FDA regulations really do not allow any automated control of devices from these remote displays or any sort of coordination that's provided by the electronic health record. Now, there's some slight caveats to that, but in general, this is sort of the baseline. One-way flow of information across some sort of networking environment to either heads-up displays or an EHR. And so the question that we want to ask is, well, if we could change this picture just a little bit by enriching this networking platform to allow hosting of applications that could do interesting things with these data streams, where might we be able to go? And so on this slide here, I have a very simple example. So the main point to realize is that medical devices, when they're designed these days, they're really designed to be standalone. They have no context awareness. They don't understand which devices they're working with, and so they're unable to detect if other devices might interfere with them, and they're unable to sort of cooperate with those devices to provide more focused or synchronized information. And so the first thing that you'd like to be able to do is to have a little bit of logic in your platform here that would allow you to do, for example, sensor integration or sensor fusion. So, for example, both of these devices here deal with respiratory function, and so you might want a little logic alarm here that would say, look, if I see the respiratory health on both of these devices deteriorating, then I'm going to raise an alarm, and that would allow me to, for example, avoid false alarms that you might get when you're only looking at the devices individually. So, you can keep on telling this story, and each time you tell a different verse of the story or different chapter of the story, you can step out in terms of your functionality. So, for example, the next thing that you might want to do is to provide some sort of control of these devices to ensure greater safety. So, this slide has a really sort of interesting but somewhat horrifying situation that occurs when you're doing throat surgery on a patient, where you have a laser that's cutting some sort of problem area or cauterizing it in the patient's throat. And in that situation, you usually have an oxygen tube that's going down the patient's throat because the patient is under sedation. And of course, if you mix laser, heat, and oxygen, there is a fire hazard. And so if you Google tracheal tube fire hazard, you'll actually get pictures like this, and even pictures where patients' faces have been burned. And the article that I've quoted at the bottom of this slide here indicates that around 1 out of every 100 operations like this results in some type of fire situation. And so what you really have here is a situation, again, where the devices are not context aware. The laser doesn't know that it's being used in association with the oxygen hazard, right? And what you want to do is to do something in an automated way like clinicians currently do now. So in this context, what clinicians would typically do is whenever they're going to turn on the laser, they manually reduce the oxygen concentration that's flowing through the oxygen tube. So if there is a slice in the oxygen tube, then it reduces the chance of a fire. And so if you have the ability to integrate devices, then what you can actually do is to at least enforce a system invariant, right? You would at least be able to say the clinician is not allowed to use the laser if the oxygen concentration rate is high, right? So again, this is, if you're able to bring pieces of this clinical space together and control their actions, you're able to do systems engineering and enforce a systems invariant, preventing yourself from getting in the hazardous state where the device is, one device is operating with another that it might interfere with.
So,
yeah.
One quick question. And the reason for that is each device is separately certified.
Separately certified, and manufacturers focus on providing the functionality associated with their particular device. Each manufacturer on their own, it's hard for them to predict all the situations where their device might be used in context.
Right, and they would probably be happy to create on their own integrated devices, which they do.
Right. They create integrated devices, but a lot of times, again, those are one-off and they can't be sort of componentized and easily sort of have their components switched in and out in a flexible way.
Right, which is kind of the old style in the avionics.
Right, right. Exactly. So it would be even better if you could have not only this invariant enforcing algorithm, but also a situation where you could have a little script run that would allow the clinician to say, I'm going to turn on the laser now, and then this little app that we have here sitting in the middle would automatically reduce the oxygen concentration from the ventilator. And if that's not satisfied, then it would disable the laser. And you might imagine then also reporting some sort of alarm to the surgical team if this invariant if the clinician tries to violate this invariant. So, again, this is just enforcing a system invariant, which we can do now when we start to integrate devices. So the final little example that I'm going to show you is one that's being used quite a bit in the context of standards development, and that's implementing another sort of safety lock, but the complexity is a bit greater. So this is dealing with a situation where you're using a PCA pump. So a PCA pump is commonly used after a patient gets out of surgery and they need some sort of pain medication. And the way that it works is there is a basal or base flow rate that's given of morphine, but then the patient also has the opportunity to push a button like this to get a burst of morphine. And so as you might imagine, there are a number of safety issues associated with these. There's even situations that you might not think of where it's called PCA by proxy, and that is where the patient's family that's in the room sees grandma there, grandma's grimacing and not feeling very well, so they push the button for her, right? And so you can have situations where you certainly are able to get in a situation where more opioid is given than you would like. And these pumps include some basic safety features like you can only press the button every so often, and there's a limit into how much you can infuse over an hour and so forth. But even with these interlocks built inside of the device, there's a number of things that you potentially could do in an integrated device situation. So even as far back as 2006, here's a newsletter from an anesthesia patient safety foundation where they said, look, if we had the ability to take information from sensors that was able to detect, for example, if a patient was moving toward respiratory depression, we could automatically shut off the pump. Now, this is something as systems engineers is blindingly obvious to us. You know, you've got the sensors there. Right now, the clinician would have to look at that and say, oh, something is not going well. Now let me walk over and turn off the pump or change the flow rate of the pump and so forth. And it's just a simple matter of trying to stitch these things together if you had some sort of platform that would allow you to do that. So in this situation, what we'd like to be able to do is to take sensor data from both of these devices as well as the alarm information that these devices are producing, have some sort of app logic here that says, look, if I can tell that the respiratory health from both of these devices indicates that the patient's respiratory health is deteriorating, I can, disable the pump, or perhaps even in more sophisticated situations, change the prescription or the flow rate of the pump. And then you can imagine, again, forwarding the same information to a remote monitoring station, where the nurse's station, for example, where a nurse may be monitoring a bunch of patients at the same time, and so forth. So, again, the problem is, in the medical space, not only are we lacking sort of technology for having this platform approach, we're lacking interfacing technology, and this is something that the folks from NIST who are on this call also work on. And we're also lacking standards that allow these systems to be safely evaluated or evaluated for their safety and security, and then pass through a clear regulatory pathway. And so what I'm going to do now is briefly talk a little bit about the technology philosophy behind the approach that we're taking in the context of what we call a medical application platform. So a medical application platform is a safety and security critical real-time platform for integrating devices, heterogeneous devices, meaning devices may come from different manufacturers, medical information systems, as well as information displays and communications infrastructure. And it's not only networking, it's hosting of applications that provide medical utility via the ability to acquire information and update and control integrated devices, IT systems and displays. It also provides a rich graphical interface windowing system that the clinician can use to interact with the system and the apps that are running on the system. Just to reiterate the concepts, you have a network with devices coming from different manufacturers. You have a platform that perhaps you have a collection of apps stored in an app library. The clinician can come in and say, oh, here's a particular workflow or scenario that I want to automate, like the laser surgery one or the smart alarm monitoring before. Here, begin the PCA monitoring infusion, and the system would check to see if various preconditions necessary to run this app safely are satisfied, and then the app would be launched. And it might do things like acquire exclusive access to some of the devices that are on the network, and so forth, and then you would get your execution. So, underlying this, we're assuming various technologies like publish, subscribe middleware that provides different types of real-time safety guarantees. But even using that base technology, which exists and has existed for quite a while, there are a number of sort of characteristics that we're aiming for in this medical space that you often don't find in other safety-critical areas. And so I'll just briefly mention a few of those. So what is the baseline, again, in terms of systems that you see on the market? So here's a system produced by Philips called IntelliView. It looks like it's integrating various sensors in a single heads-up display, and it is. It is modularized to some extent. If you can see the box that's down here on the right-hand corner, it's got these pluggable modules that are color-coded that provide various sorts of pulse oximetry information, heart rate, respiratory rate, and that sort of thing. Why is this not a medical application platform according to our definition? So first of all, we want our platform to be open and extensible. So here this system was built and designed to work with products from a specific vendor, namely Philips' own products. All right? And then they also had a few contracts with companies like Masimo and Nellcor to provide some pulse oximetry components. But it's designed from the outset to be sort of a closed system working only with their components. It also doesn't provide any way to extend the functionality or the application logic. It's just basically displaying information here, and you're hard-coded with the functionality that comes built into the product. So for us, the types of things that we're interested in are enabling interoperability with heterogeneous components, components coming from different vendors, all right? And the challenge here is that these different vendors may have different quality management systems. There's going to be tension between acceptable risk management that they're doing on their own side and how much of that risk management information they can expose to people that want to do the integration and the overall reasoning about the system space, right? And so that's one of the challenges, is moving into the context where you're dealing with heterogeneous components.
Oh.
Yeah.
One question. So in in, an FAA type environment, you're really certifying a system.
That's right.
You're not certifying simply the software, not certifying the hardware.
Right.
You're really certifying it's this version of the hardware,
right,
this version of the software, which then, to some extent, if you start talking apps, an app may have this version. On the other hand, it may be upgraded.
right,
And if you're looking at a certain Apple version, just because I'm getting this app by this iPad or whatever, it may have some different elements than even a slightly earlier version. There's not necessarily the level of control over every single component in the system.
That's probably true of any software-intensive system that's included.
Right, yeah, exactly.
Over time, and that's what I was wondering about.
There will be, I will try to address that issue as we move along, but basically the idea is you have to write standards that control the ecosphere from which these components emerge, and you need various technologies on your interfacing to make sure that the needs of the application are correctly met by the service components that you see on the platform. But I'll talk a little bit more about that.
I would also suggest that you need to have the protections in place to prevent misbehaving by some of the components from adversely affecting the others.
Exactly. That's one of the key technology components that I'll talk about in about 10 minutes. So another feature here that we'd like to be able to support if possible is allowing maps to be open and extensible. So just like you get your phone, you buy your iPhone, in October 2013, some new cool app comes out 3 months later, you can download that app that wasn't envisioned or wasn't even in existence when you bought your phone. All right. So the question is, can we imagine a safety-critical platform in the medical space that can be brought through a certification process and deployed, and then later on after that, people can develop an app and run it on the platform without you having to recertify the platform and the app together? That's basically what I have in text here. When most conventional critical systems are deployed, the set of possible constituents is known in advance. In our system, we want to be able to allow the infrastructure components to be deployed and then subsequently use new devices, new device types, and apps that were not anticipated at the time of deployment. At the time, you also went through V&V and regulatory approval of the platform. So there's some silly little example here. I build a platform, but then somebody comes out with this sort of mind control device here, and I should be able to write an app to control what parts of the memory get wiped. I mean, maybe Brad might be interested in this sort of thing. I don't know. The idea here is, how can I possibly do that with a platform that's already being deployed? And the idea is that you want to have very sophisticated technology related to your interface description. So if you have an interface definition language that allows devices to describe their capabilities along with their quality of service and even how they may be propagating different types of faults, you have an app language then on the other side that app developers use to state their requirements. And then because the platform itself is designed to work with any sort of device that can be described in that IDL, right? Then you have the ability to support devices and apps that emerge after the platform was originally developed. So that's another key concept in what we're doing. So let's turn to an issue that Dave raised. What exactly are you certifying in this context? So I have to give you a preliminary definition here. So what we call a map instance is an instantiation of the map architecture. That is, it's a selection of a specified map hardware components that conform to a particular architectural standard. And so the idea is you want to allow somebody to say, okay, I've developed an implementation of the platform that corresponds to the standard. And then someone else can say, well, okay, we've developed these devices that conform to the device component or form of the standard. Together, right, these form a particular instance of the system once I start to put my application on there. So the question is, what should we try to regulate or verify or set up standards for? Are we regulating the architecture? Are we regulating instances of the architecture? Are we regulating sort of all possible instances that might work to support a particular app? And what exactly constitutes the medical device in terms of existing regulatory language? You know, we have a whole body of regulations that call out specifically a definition of medical device. How do the pieces of the puzzle that I'm showing here relate to that particular definition? So on this slide is the way that we're thinking about it, and that is the device that you're actually interested in regulating is what you get when you compose the app onto the platform with a particular selection of devices. So, you know, going back to Dave's question, what is it, the exact system that we're regulating? The system is constructed when you take the devices, compose them with a platform, and run an app on it. That defines virtually a system whose behavior you're responsible for reasoning about the safety and security of. And so that is the challenge. So no one of these, oops, I've got a little bit of a lag in the slides here. No one of these entities defines the behavior of the system alone. They each contribute behavior to the composite system. And it's important to note that in our view of the world, the app plays a special role. In other words, it is the thing that specifies the composite system behavior, and thus it is responsible, the app developer is responsible for making the overall system safety argument for the systems that it will generate when it runs on the platform.
Comment?
Yep.
This is Chuck Kilgore from the FAA. A slight clarification on a previous commenter on certification of FAA software and hardware, that type of thing. Actually, there's only a certification of an aircraft, propeller, or engine. Everything else is approved to fly on a certified aircraft, propeller, or engine.
Yes, okay. So the long-term vision, and it's unclear if we're going to be able to get to this, is a situation where you can have a standard for a platform, and Hospital A could be running a platform implementation for one vendor, and then they could be running an app that's using, for example, a GE device and an L-Core device, right? And then Hospital B is running a version of the platform for another vendor, right? But it's running the same app and using different devices. So you can see that if you're thinking about an app's responsibility in the systems that it can generate, it can really generate a family or a product line, just in some cases if you want to think about it like that, a family of systems, but all of those systems would have to satisfy assumptions about both platform and devices that it states or captures on its interface. And so there's a number of interesting twists here that have to be considered in the safety evaluation and regulatory point of view. So yeah, let's go to try to draw some connections with avionics. And this is, again, I'm oversimplifying the case in some degree. But what you have in the avionics context and other safety critical systems is that integration is performed by a prime contractor that's responsible for the integration and system level V&V. So integration of components to get your system is performed before deployment with a full knowledge and behavior of the components being integrated. The integrator has expert level technical knowledge of the components and system behavior, right, and is responsible for the overall system V&V safety arguments and certification. So you have your typical V diagram like here, and the end-to-end process is managed by the prime contractors to some extent. And so what's different in this world that we're talking about is that, for one thing, in the existing space, system integration in V&V is done before the system is delivered to the customer. So in this space that we're talking about, things would look slightly different. You would have a medical device manufacturer that goes through their own V&V process, a manufacturer that's building the platform. You would have an app developer, all right? Those things actually get put on the market, and then they're deployed in a hospital, and it's actually the technical staff at the hospital that does the actual plugging together of the pieces, and the actual runtime or execution of the system is what defines the system. So you only...
Comment?
Yeah, system showing up.
One other connection to the analogy here of the aircraft would be that when an aircraft gets type certified and it's being flown, and then some software wants to be added on after it's been type certified, it has to go through an approval process also, and it's at that stage where it's included in the airworthiness side of the flight standards part of the FAA.
Okay. If you could possibly email me that concept, that would be useful for me.
Okay, what's your email?
If I can give it to you, or Ernie can...
I can send it, Chuck, I'll send you his email.
Okay.
Okay, Ernie, thank you.
You're welcome.
So what's needed is a new regulatory approach and a new approach for safety standards in this space. The way that it works is you may have an integrated system, like here's a clinical monitoring station which is integrating a number of different devices in a number of different rooms. Again, if you add a new device, now you have to sort of go through entire regulatory clearance again. Now there are some exceptions which I'll acknowledge on the current slide, but we can see that if we want to enable this type of platform approach, if you force people to follow this in a strict way, you're not going to develop the market and the business case that would be necessary for people to develop systems like this. So in the current pairwise regulatory approach, when you would add a new app, the scope of regulation would be the entire system. And for example, also when you add a new device, the scope of regulation would be the entire system. And so we want to see if we can come up with some cases, at least. We may not be able to get this to work for all cases, but we would like to be able to have a situation where someone could write or build a new device that could be integrated without having to recertify the entire system, especially the complex platform.
So are there, in this certification,
Yeah.
are there different levels as there are in the FAA?
Yes, you would have different levels of criticality,
Okay.
or safety integrity levels, or whatever you want to call it. Now that we haven't completely designed those yet, but that is the vision.
But what is it today?
Today, they do have different levels of criticality. So, for example, if you have an MDDS system, like I showed you before, and it's just forwarding data, in those situations, you can add new devices without having to recertify the entire system.
Part of the environment of this thing would include the whole medical staff. And I'm just wondering, are there assumptions about that they do things in certain ways?
That is a great point, and part of the standard that we're writing, and this is the group that Sandy Weininger, who's on the phone, is leading, is coming up with a way where you not only reason about sort of the engineered system, but you also reason about the safety properties of the staff as they're interacting with this. And the sort of consensus that a lot of things that this type of system would need to do is to perhaps monitor the workflow of clinicians, or at least have various preconditions that are checked before you launch an app to make sure that the appropriate things have been set up correctly in the context. So that is a big part of the problem. So in this case, this relies on for the device being able to appropriately declare its capabilities in some way, to declare its hazards and safe states, and you want to be able to do things like check to make sure that it implements the appropriate networking protocols and so forth. On the app side, again, if you add a new app, you don't want to have to certify the entire platform again, or even the systems, all possible systems that the app could work with. You'd like the scope of regulation to just be the app, but the app, of course, would then need to have a number of properties, and the system would have to work with those properties. So, for example, the app would need to specify its requirements for the devices and platform capabilities. So for those of you who are familiar with these types of systems, I'm talking about resources that the computational platform would have to provide, bandwidth requirements for moving the data, worst case execution time, and so forth of the app. And the app regulatory submission must also provide an overall argument for the safety of the constituted device. So our research is exploring the extent to which this is possible. We're not claiming that it's possible in all cases, but we're looking at the platform technology, also the risk management, safety, standards, and regulatory context. So, you know, a lot of people are rightly, skeptical of the extent to which this approach can be put forward and still ensure safety. So one argument that sort of speaks to those concerns and answers the question, well, why even try this, is the following. So currently, the safety and engineering principles for determining component-wise review, when it can be applied and when it should not be applied, are unclear. So I'm talking about in current FDA practice. So currently, the FDA permits some notion of component-wise review, and the decisions are made on an ad hoc basis, so there's no explicit statement of the safety principles that justify when such an approach can be taken. And so this creates uncertainty in the vendor space. Can I apply this to my product? Is it worth building my product in a componentized way? And what steps would I have to take to allow my product to be reviewed in this way? What would be the safety principles that I would need to consider when I'm designing my entire risk management process? It also creates uncertainty on the regulator. You know, what exactly do I look for in this submission that wants to do a component-wise process? And on what technical basis should I grant approval or deny approval? And so really, one of the things that our research is doing, both on the technology side and the standard space, is trying to clarify when component-wise reviews should be allowed and when it should not be allowed. So now let me speak a little bit to the underlying technologies involved. So we're working with a standard for an architecture, and it's just a very thin standard that defines the functional components or layout of a system. And I'll step you through some of the pieces, and people that work in this area in the security space will immediately sort of connect with some of the functional goals of these components. So this is an ASTM standard. It just specifies essentially the blocks in this architecture without defining the details of their interfaces. But this standard is the focal point of multiple subsequent standard activities, and it's the only such standard that's recognized by the FDA at the moment. So that's one of the reasons that we're working with it. So the first component you see is the application hosting component. And if you're familiar with the concept of a separation kernel, it either appears in the middle security work or, for example, in the context of flight software like the operating system that runs on the F-35, for example, the strike fighter, it includes a separation kernel. And it includes strong space and time partitioning of the apps that are running. So someone on the phone mentioned before, how do you control interactions between the apps? So this is one of the pieces of the puzzle that you assume. You assume the supervisor provides functionality similar to a separation kernel. So it also provides application program interfaces for clinical displays, determining what devices are available to use on the network, exchanging data between apps and devices, and so forth. It also includes a fault notification system, so when you're getting like an unanticipated device disconnect or failure to deliver the appropriate quality of service, there's an entire sort of messaging framework that's specified where apps and the supervisor itself can be notified of the failure to achieve the specified QoS properties, and you're notified to take appropriate action. I won't go into the details of that. There's also runtime checking to ensure that the apps are well behaved in various ways and don't interfere with each other in unanticipated ways. So the network controller is. The network controller is, again, you can think of it as middleware. We're currently using a publish-subscribe middleware, but it also provides strong partitioning properties and management of QoS. So we view this as a high-assurance network which provides services to support communication between the apps, devices, and health IT systems. Again, the approach that we're taking is built on publish-subscribe. Some other people are looking more at web services type of architectures. Keep going on here. All right, so again, back to these key properties that ensure partitioning. So a primary concern needed to support component-wise reasoning is partitioning. So specifically, the platform architecture needs to provide guarantees that all interactions between hosted resources are limited to explicitly declared interfaces. So this allows us to reason about the safety, for example, of one app without having to worry about the actions of another app. So we need both the partitioning properties for the apps and the network so that if an app understands what it needs in terms of bandwidth and latency and so forth, it can rest assured that the platform is going to guarantee that without interference despite any other apps that you choose to run on the platform. So what happens in our system is there's actually a flexible or dynamic partitioning. So I'll have some graphics about this in a second, but an app requests as part of its specification states the computational resources that it needs to run. It also states the resources that it needs from the network, and the platform will guarantee that. So then if you run, and then so you can reason about your app in isolation, because in essence it doesn't matter if you're running with something else or not, because the platform guarantees that you're isolated. So then if you put another app on the framework with a different set of devices, even devices that overlap, the goal is that the platform will ensure that there's no harmful interactions through the system itself. Now, you may have to worry about harmful interactions through the environment. One device may act on a patient, and that interaction may flow back into other parts of the system, but that's a separate issue. The way that we also have set this up using the technology that's been developed as part of the team that we have at UPenn, you can actually get this sort of functionality and also include on the same work non-critical hospital IT traffic. And the way that this works is using OpenFlow technology. So the idea is that with this type of framework, you can use conventional Ethernet, but you just change the switches to use OpenFlow, which is a switching framework that allows you to, in essence, customize on the fly through interfaces that can be accessed by the framework itself. So it provides the timing guarantees, and it provides an open, a publish, subscribe middleware that's based off of OpenFlow. Here's some of the key concepts, which I won't dive down into the details, but you have control of low-level packet forwarding rules, so you can install per flow. So per flow means from a device to an app, for example, from the producer to a consumer. You can install per flow rate limiters. You can differentiate traffic in the network. You can learn the physical location of nodes in the network at runtime. So forth and so on. And now these are provided by a number of vendors, so if you want to run this type of system in a hospital, the idea is that you should just be able to go into the hospital's networking cabinets, which also include these switches that can support this protocol, and just change to run the OpenFlow protocol.
On the on the VM,
right?
Virtual machine. So is this sort of like VMware, where you're going to be creating virtual switches, virtual routers, virtual apps for testing and so forth?
You can do that on the supervisor platform.
Right.
The OpenFlow here that I'm talking about,
I was talking about like 2 slides back.
Yeah. So it of course runs in sort of a virtualization mode by default to gain the separation properties that you're interested in.
Are you able to do testing through a virtual machine, as far as being able to set up a virtual network and have virtual apps, virtual devices, and so forth, and be able to test and see how they interact and play together?
You should be able to do that, yeah. We haven't developed the testing infrastructure out at that level.
Because that would make a lot of sense if you could do that from a practical perspective, be able to proof of the concept.
Yes. So here's a little use case of how things might work in this framework. So imagine that I have a device. It wants to hook up to the network. One of the things that it'll do, this is extremely simplified, but for example, it says, I'll publish, and it declares a particular physiological parameter type, and it also says information about its, its QoS or performance. So it says, I'm going to publish at a certain rate. That information flows to the resource manager that then configures this switch to make sure that the device, for example, doesn't publish faster than 60 hertz or else it gets throttled, right? And so then once that happens, you may then on the app side have a situation where the clinician comes in and launches the app, and the app might say as part of its requirements, I want an ECG data stream that comes at least 50 hertz with a max latency of 2 milliseconds, right? And so that information is also forwarded to the resource manager, and the resource manager configures the switches on the network as appropriate. So because you're sort of dynamically setting up to enforce your different QoS and partitioning properties, if you have something come in, for example, that's trying to do something bad on the network, first of all, the way that we set up an authentication framework using digital certificates and so forth, this guy would never, ever be able to connect. If you have a situation where a good device connects but then starts to malfunction and delivers its data out of range of its quality of service specification, the rate limiting and so forth at the switch itself prevents that information from flooding onto the network and so forth. So that's a sort of a brief overview of how this dynamically controllable open flow switching technology is being used to set up this partitioning and QoS enforcement on a standard network.
John, this is Paul Miner. On the switch itself, is there any internal redundancy to protect against failures on the switch not enforcing these rate mechanisms that would then lie latent for some time, and then it would be vulnerable to a second failure in the system?
Yeah, so we don't do anything with that now, and since that's not my area of specialization on the project, you might want to check with the UPenn people if they have an opinion about how that would work, but we do not do that now, but that's something that you could conceivably set up as a failover on with redundancy on each switch, as far as I would understand.
Yeah, I mean, that would be how it's done in some of these similar types of switching capabilities in current generation avionics,
Right.
AFDX, for example, or time-triggered Ethernet.
Right, yeah.
So, how do you, one of the questions that you always have is, when you're doing certification of
Right.
there are always standards and
Right.
a set of requirements that if you're developing code to level A or level
Right.
B. So the question would be, so typical university wear
Right.
is not developed anything like this.
Right.
So we're not the middleware that you're planning to, that would be a good candidate for
Right.
integration would have to be developed in accordance with some.
That's right. That's right.
It probably wouldn't be the Midas.
No, for example, what's happening is we are, in conversations with various middleware vendors like RTI that makes DDS, because the framework that we set up could be easily made to be compatible with the DDS interfacing standard. And so you would want to partner with
Right.
an industry partner who would take on the full burden of doing the full certified development process. So, okay, somehow the slides are not advancing. Yeah, I know. I mean, I'm advancing them here locally, but
Did you lose the WebEx connection?
WebEx is still on. I turned on my iPads are still working.
There's an interoperability
issue.
So you are able to advance on your?
Yeah, I can advance on my side.
You can advance on your computer?
Yeah.
Is he still the presenter?
He's still a presenter.
Okay, why don't you fire up your slides, make yourself the presenter, and go to slide 42.
42. Let's do that.
You might want to get out. Anyway,
Yes, you can get started easily here.
Each slide is.
They won't see that's what I'm doing right here.
Oh, okay.
Okay, let me know when to stop here. Am I going too far?
Nope. Oh, you got a ways to go.
There we go. Now we're getting close.
Yeah. So next, right there.
Right there? Okay, you've got the controls here. Let me put the,
Just give me your mouse or something.
it's over there. Let me turn it back to Joe.
can everybody see something that looks sort of like a UML diagram?
Not yet. Hold on a second, 1 second. Share my desktop. There it goes.
Now I can.
Okay, great. And so one of the questions that's going to come up is, well, what sort of rich interface specification language do you use to allow an app to specify these different quality of service requirements and essentially the capabilities that are needed from a particular device? And that's all part of our research and is somewhat related to what the folks at NIST, including John on the line, look at. And what we're trying to do is, in essence, think about what it would take to extend things like 11073 interfacing technology to support the type of dynamic and secure type of interactions that we're talking about here. So if you go to the next slide, or great. So what types of things would you expect to show up on these interfaces? So not only things that appear in the existing 11073 interfacing language like physiological parameters, alarms, device settings, and so forth, but also improved quality of service information, security controls. You want essentially a behavioral interface specification language that allows you to state pre- and post conditions, and also be able to give risk-related classification of parameters, including things like faults that might propagate out of the particular components. And so you can see on this slide here, I'm running behind time, but there's ability to have notation that declares that sort of thing, the different types of communication patterns that you're using, so that the system then, when you come to figure out, try to figure out, well, is it possible or is it a good idea to run an app with a particular device? An app will state its requirements in this language, and then the devices also describe the capabilities that they provide on their interface. And then dynamically, when the app is launched, the platform will check to see if there's a match between what the app requires and what the devices can provide. And so some devices, of course, you may choose to rule out because their capabilities don't match, or, you know, you're also the things that they've reasoned about with versioning and so forth. That's also where this type of information would get exposed. So overall, this is one of the most important slides of the whole presentation here. How do you make this work in practice, and what are the main principles? So the idea is that an app declares its requirements for devices. It also declares its requirements on the supervisor and also on the network controller in terms of the bandwidth needed and so forth. And you have a priori third-party certification to check to see that the correctness of the app or the safety of the app, if possible, can be established under those assumptions. And then, okay, I've got here annotations that say what you need to state on what you need to require the supervisor, scheduling units, unit period, memory requirements, and so forth, bandwidth and latency on the network controller. And then on the device side, you say what capabilities you require, and then what happens is when you launch the app, you check these different conditions. Is the supervisor currently able to meet my computation requirements? Is the network controller able to schedule me, right, schedule the communication that I need? And does the device provide the capabilities that I need? So if those all are met, then the app gets to launch and run. And so the vision for all of this is to coordinate the development activity for an app in an integrated development environment where you would be able to help them specify all of that information and then apply various types of tools that help them write requirements, do hazard analysis, risk assessment, and so forth, and also package up things in a form that would be submitted for certification authorities and, for example, part of a FDA 510K submission package. And we're using sort of component-based technology that was derived from our earlier work on the Bold Stroke project that sits on top published subscribed middleware, but we shifted to use AADL, the architectural analysis and definition language. One of the reasons that we're doing that is because it's an industry standard. So you can see some of the layout of the components there. AADL also includes an error modeling language that's essentially a form of model-based hazard analysis. So you can do things like declare your failure modes for particular components, You can describe where faults might originate within the system, how those might propagate, and then other components declare whether they handle that sort of error or fault or not. And in essence, different forms of type checking and static analysis help you automate a lot of the activities that you would typically go through with things like FMEA and FTA and so forth. What we've been doing is not really relying on FTA and FMEA and those analysis, but integrating Nancy Levinson's STPA approach within the framework. So I'm realizing that I'm probably gone an hour now. I've got a few more slides that talk about the standard piece of the puzzle. Do you want me to cut that off and just take questions, or do you want me to?
When we go 15 more minutes.
Okay.
I don't think I've ever been in a meeting where any presenter's been spot on time because of questions and so forth, so I'm game.
Okay.
I say keep going.
So I'll briefly walk through the work that's been done on the standard. So the goal here is to try to set up a family of standards, not just a single standard, that would enable this type of system to be built and put on the market and would clarify the regulatory pathway both for vendors and for regulators. So the theme is to try to do something that would allow component safety claims to be stated in the context of system safety, and then allow to be components to be assembled within an architecture that constrains interactions. So it's extremely important from the outset to realize that the theme of this standard is you cannot just come in and say we have a system that we want to take through a component-wise verification process, because the architecture of the system is key to making the whole thing work correctly and to provide the basic foundations for safety. So, for example, without the partitioning requirements that I talked about before, without the partitioning capabilities of the network, without the ability to declare your QoS properties and have those enforced by the system, you would not be able to approach confidently a framework that would allow you to do component-based development. The standard also emphasizes that you have to not only specify the architecture, but you have to specify the ecosphere, including the life cycle processes that the platform goes through under development, exactly when the gating occurs with respect to your safety claims, and so forth. So intuitively, you want to be able to describe components and their interfaces. You want to use an architecture to constrain the interactions, and then from that, in cases where it's possible, which should be described by the standard, you want the ability to be able to infer properties about the overall system safety and security. So how is the standard organized? And this is something that I would really appreciate feedback on because to me, it's a very interesting challenge. So what we want to enable is interoperability in the medical space, not just for one particular architecture, okay? And so the thing that we're trying to do is to come up with a collection of architectural independent requirements that sort of state properties that any interoperable system should have, risk management process that any interoperable system should go through, and so forth. And those are general requirements. So these state, again, safety, security, and essential performance, common vocabulary for referring to elements of interoperable systems, general construction and architecture, interface specification requirement. What's the general way you should define an interface? What's the general risk management approach? There's a library of common faults that are used to seed your things like FMEA and so forth, general testing requirements, and so forth. And then the idea is, if you're a particular vendor or group of vendors that wants to form, in essence, an interoperability ecosphere, you come and you propose an interoperability architecture that describes the safety principles that that architecture enforces, along with the life cycle processes associated with that architecture. So there will be guidelines for how you define your interoperability architecture and your interoperability ecosphere. And so you can come in then and define for a specific architecture how that architecture should be organized and so forth. So that will allow the standard to support multiple interoperability architectures. Then there's also a dimension on the application side. So down this vertical dimension is where different common clinical scenarios that we want to standardize are picked out. And you describe the overall safety principles, top-level safety principles and hazards for that particular application domain. And again, there's a process for how you introduce a clinical scenario, and then there's specific clinical scenarios introduced. And then finally what you can do is say, well, I want to use this platform here to implement a particular clinical scenario. So you get the context information regarding top-level hazards brought down to here, and then you reason in terms of your particular architecture safety features that are guaranteed here. There's a standard that would describe how those pieces are brought together. So this is a somewhat complex family of standards, but if you're familiar with things like 60601 in the medical space, it also has various notions of hierarchy and specialization and customization along different dimensions. And so there's a pretty broad group of participants involved in this, some of which I put on the slide here. I either want somebody to ask me a question, or I want to propose a question for myself that will allow me to describe a couple of other sort of strong relationships to other domains that people on the phone are involved in. But I'll just wrap up at the moment by saying what we're aiming for here is this medical application platform concept that can enable rapid innovations in clinical system functionality. You don't have to build new hardware. You don't have to come up with new displays for your hardware. Logically, you just develop your application logic as an app. It can use the same hardware that's provided and shared across multiple applications. The technology exists to build these types of systems, but really the lack of architecture, interoperability, and relevant safety standards creates barriers. Vendors just don't know how to bring these to market and navigate the regulatory process at the moment. The regulatory pathway is not clear at the moment. So work such as ICE and the people that we're collaborating with, we're not saying that we can provide all the answers, but we're working within the industry to develop a consensus around the important architectural safety and security and ecosphere requirements and develop a path forward for addressing the challenge. And there's a rich potential for cross-fertilization with other domains. Things like the mills, and it's the way that its certification was set up originally using common criteria, integrated modular avionics, and so forth. And so that's, I think, some of the things that I would like to consider at least a little bit in the discussion.
Do you have your standards group? Do you have participants from folks like Philips? Because you mentioned they already
Yes.
have their sort of.
Yes. So some of the major vendors include Philips and GE and Draeger, all of which intend to bring systems like this to the market.
So speaking, so speaking from a tactical perspective, I worked for EDS for 10 years, and I managed the medical networks for the Air Force and the Army in Europe.
Right.
We ran a number of different applications. Here you're talking about taking various medical devices and putting them, essentially putting them on the network, correct?
Right.
So would you, I'm just thinking from a network administrator perspective, would you have to create subnets, reserve bandwidth, all the rest of these things for these applications to run smoothly and effectively? And further, would you have to create a VPN between the devices as far as within the network for patient security, network security, those sort of things?
Yeah. So again, there's various ways that these systems could be deployed, and it depends on the level of criticality that you want to support, obviously.
And the other question was,
but the main partitioning guarantees that we've developed as part of this would allow you to, for example, run these devices in isolation, but still be on the same network as the hospital traffic.
Right, correct. The piece about lack of architecture, are you talking about lack of network architecture or lack of bandwidth?
More lack of system architecture around the way that you integrate devices in the health information system. So, for example, here's the bad thing that people are currently doing. Health information systems where you keep your electronic health records are quite sophisticated. They often come with rule-based languages that allow you to program up various types of logic. You know, if a patient comes into the hospital with this condition, then these alerts are triggered and so forth. Right. So they're using that rule-based language to try to program these sorts of medical clinical interactions between devices. So they're using a completely non-safety critical framework where they're not setting up to ensure any of these partitioning requirements or reason about non-interference. You know, people are starting to use that. So that would be an example of a poor architecture.
Right.
Right. So what we're trying to do is...
That's what I kind of thought you were coming from.
Right.
So will there ever be a, you know, so part of the thought here is to really create a larger ecosystem.
Right.
Yet there are kind of major obstacles to really being part of the ecosystem in terms of the discipline development that you have to do, which is still very different than what apps.
Right.
Yeah. I mean, it's why in avionics you still have a relatively close community.
Right.
You know, do you think we'll ever get to a stage where...
Well, that's one reason why, as part of our research, we've always emphasized the idea that you want an integrated development environment, like I showed you, that you deliver with the platform to ease the burden for doing all of these things and to ensure regularity across all the different apps that are developed. Plus, if you have that same environment, also provide tools to the reviewers, right, who now, instead of having to look at submissions that are built with a huge amount of variability, the regularity is enforced by the development environment itself, so that these apps can be reviewed much more quickly.
I could imagine your development environments targeting, say, subject matter experts, so you could bring in doctors, nurses, other specialists who would be able to allow them to describe the apps that they have in mind and still meet all the safety requirements. I mean, is that sort of a goal?
That is, again, part of the reason that we're developing this development environment, to have a model-based view where you can imagine different widgets that they would pull together, and first being able to simulate those interactions.
So you're not depending on hero developers of whom there are never enough.
Well, you'll always do that to some extent.
So, I mean, not that you're going to exclude them, but...
No. I mean, the way that, if I were designing the perfect system like this, I would have a framework where a clinician could program up the expected workflows that they're expecting to follow in their context, right, in their caregiving, and I would have that married with, the ability to quickly stitch together and simulate the logic of the system. And then they would be able to model check or simulate the contextual interactions with the application logic.
Now, issues would be reported back to them in a language that makes sense to them.
All right. Could you page through about 5 more slides there? I have some I have some interagency issues that I'd like to just toss out there. Keep going, keep going, keep going. All right, there we go. So a couple of things that I wanted to bring up as a message to the different agencies that are involved here. There's a lot of emphasis, and the CPS program has been great, but really the focus of that program has been the technology dimension. And what I'm finding is now in the work that I'm doing, I'm spending roughly 10 to 12 to 15 hours a week working on just this standards activity in the regulatory side. And the issue is that really that type of work is somehow needed to be able to bring these systems to market. And as we get into a situation where CPS is employed more and more in automotive, other domains, beyond just the medical space, we're going to need to be able to take the technologies that are being developed in the program and be able to make arguments about how they would be run through a certification regime. And so things like current standards, regulatory regimes, safety assessment, whatever, they can't really support the types of complexity, system composition, and reuse and dynamic integration that are currently being supported in the CPS technology program. Right? So somewhere you're going to run into a barrier. We're going to fund people to build all this cool stuff. You go to transition into practice in regulated domains. There are going to be these dramatic barriers. So that needs to be addressed.
Well, in part we address that with our at least the first start is our TTP option that we've brought into our program.
Right.
And actually have funded, I think, several projects with that this year.
Okay, so that's good. So I haven't been aware of things like that being funded before. Another thing that I'd like to mention is a lot of the concepts that I talked about, as people have suggested on the phone, tie into things that are being developed in other domains. So I'll pull out specifically the Mills architecture and the way that people like Rance DeLong and John Rusby envisioned the common criteria being applied to certify those types of systems. Now, due to various political reasons in the U.S. government, I understand the common criteria has sort of been de-emphasized, but there is a lot of good work there that should be shared over and applied in the medical space. And then as these medical systems are emerging, you know, there's a lot of technology that could be pushed back over across domains. And I'm just not clear, you know, who are the types of people that are going to be funding that sort of bridging activity of standards, and how can that be facilitated? Because for me, when I go into these standards committee, I'm dealing with people that are conventional developers of medical systems. Right? They do not understand the concept of a platform and how to set up platform engineering and product lines, and they certainly don't understand how to write a standard that would allow you to really support reuse in the context of product line and platform development. So to really avoid situations where we've got stovepipe technology limited to specific domains because, for example, you build something and it's set up to work with the common criteria, but it's not immediately set up to work in the context of, you know, these emerging medical standards, you know, what can we do to enable freer flow of technology innovations across domains by, in essence, being able to coordinate activities on standards development as well. Now, I've got a couple of other slides if you want to look afterward related to, again, the notion of standards for supporting product lines and platforms and listing the types of things that are sort of, that need to be addressed in this context.
I'm assuming that the work you're proposing is scale up to the level of a hospital.
Sure.
Right. I mean,
yeah.
I assume that's sort of what you're doing.
Right.
If you wanted to go beyond that to more of a regional or national level.
I mean, the way that the current ICE standard is specified, it's really specified as one platform per patient. But you can imagine that being scaled up, you know, across an entire ward or something with hierarchy developed to push information to the cloud. So, for example, the way that Cerner is a large medical informatics company, the way that their system works, they're running on top of JMS, which is another messaging system like DDS. It was a predecessor to DDS. But they have large-scale servers that support an entire hospital with failover capabilities. You know, if one server goes down, you automatically fail over to the other one, and so forth. So that's one of the reasons why we wanted to allow flexibility in the standard. So if you come up with different architectures that you want to bring forward to address this scalability problem, there are principles in place for how to sort of move forward.
So I want to follow up on that because I had a question when you were presenting the 2800 standards notions. It seems that there do not exist any sort of default architectures in this domain yet, and so you have the luxury of trying to come up with a pre-competitive architectural pattern. I just wanted to, I guess, caution that there may be distinct architectural pattern solutions that each individually would be fine, but they would not necessarily play nice with each other. And so at some point you're going to fix on a particular solution space and rule out some other things that might have been otherwise considered viable.
Yeah, so let me make sure that that you understand the diagram here of what we're doing. Well, maybe it's best just to work off this small diagram here. So again, the intention is that different architectures can be introduced. Right? And so that was one specific reason why we said, okay, we're going to take the ICE architecture, which is the only one recognized by the FDA now, and it's going to be the first one that we address. But we're going to design the framework so if you have an alternate architecture, you can use the same standards framework to introduce the definition for that architecture. Very similar to the way that the common criteria was set up, for example, to allow different protection profiles and so forth. So does that answer your question? Or are you talking about situations where you may want to take architecture 1 and then stitch it together with architecture 2?
That's exactly what I'm talking about, and I would imagine that sort of thing would be more than likely to occur in the medical domain. and that in such stitching together, they might have been designed with different architectural philosophies that don't necessarily line up.
Yes, that's perfectly true. I don't know how to solve that. I mean, that's really a sort of a long-term, I wouldn't call it a social problem, but it's you know, where we are today, there's no way to predict and take different architectures and design them so that they can plug together with other architectures that might emerge. So I guess, you know, what we're trying to do is, again, allow the flexibility for the architectures to evolve and to add additional architectures to address those situations.
Yep, and I'd like to follow on with a different question, and this is in regards to the case where you were wanting to introduce an app into the system and you had all of the sanity checks that there are sufficient resources for that app to run. And my presumption on that slide was that if there were not sufficient resources, you would not be allowed to enable that app. But it seems to me that within the medical domain, as patients' conditions can change dramatically, you might end up having different levels of criticality of apps, and it may be context-dependent what the criticality is, and you might need to have some preemption scheme where you would disable some other app in order to get this app in to deal with the recent change to condition.
Yes, that's a great point, and we have the framework in place to deal with those types of situations in a limited way, primarily around the issue of security for the moment. So there's a term that's used in the security space that you may be familiar with called break glass scenarios. This is essentially where something is going so bad you want to break the glass and pull the fire alarm. And this is situations where you override the automatic protections put in place by the system in a controlled way that essentially logs everything so you have some sort of accountability later on. So we haven't addressed that in the specific context that you mentioned about preempting apps of lower criticality, but that concept does exist primarily in our work that we're currently doing on security.
All right, thank you.
I gotta leave in 5 minutes, so before I leave, feel free to finish the agenda. So one, I wanted to make sure everyone's aware we're having our CPSPI meeting tomorrow and Friday, and I think, Sushil, if you're interested, it's at the Marriott Crystal Gateway. Send me a note. You're already registered. Yeah. I think I've pre-registered a number of government people, but if anyone here is interested in attending, it starts something like 8 o'clock in the morning tomorrow at the Marriott Crystal Gateway. Send me an email, and we'll get you pre-registered.
20:09 is the first presentation.
What's that?
8:40.
8:40, right, okay. There's, I guess, some registration and some, probably, no doubt, some breakfast earlier. And there are some interesting speakers as well as interesting panels over the next several days. And I think there are probably 10 to 12 different PI presentations, as well as a set of presentations by our large frontier projects. So you'll get a good overview of what's going on in the entire program. There's a panel on smart cities on the second day, which I think most people will find interesting and engaging, in that it will be looking at what are the real hard-hitting research challenges. And there's a panel scheduled the last day, just before it closes, that will talk about some government perspectives on cyber-physical systems, especially as they relate to the CPS program. And
I have one last question regarding your presentation, regarding the standards.
All right.
So there's a number of other projects that I'm working on regarding like comms standardizations and LMR standardization. Do you see this coming to a point where there's going to be like an FDA standard or whatever regulatory body that regulates all the devices, the medical devices, to state that as a minimum they have to meet these certain criteria that would enable them to function within this environment?
Yeah, so the way that we envision that is that that would not be something that the FDA does per se, but as part of the Ecosphere organization, there would be third-party certification set up to do the compliance testing to the various protocols.
From like a JAGO
type
of bodies?
Right.
Okay.
Because the FDA doesn't make standards themselves now. They recognize standards that other organizations develop. And so it would be the same, the idea is that they would recognize this entire framework as being viable, but they would, scrutinize the appropriate implementation of the framework and the fact that there were these third-party organizations set up to do the compliance evaluation and safety evaluations, which would then be packaged up and presented as part of the overall safety case for the regulatory claims. But any feedback that other people have on related standards that emphasize notions of reuse or support, platform-based engineering, we would be extremely interested in. I mean, the things that we're looking at now, again, would be the mills work and IMA to some extent, but I know there's more recent things emerging in the avionics community that I'm probably not up to speed on.
Yeah. 10 years ago, RTCA DO 297 tried to develop guidelines for IMA that had similar sorts of concepts, obviously not as mature because it was 10 years ago.
Yeah, I think I've even found a reference to that, and I was wondering where that went. I mean, I know there's the FACE program that also has emphasized notions of components and reuse in avionics, but I would like to meet someone that could give me more details about what's happening there. And anybody that would be interested in sort of putting together some sort of presentation or perspective about how reuse is handled in their own domain, our standards committee would appreciate that.
Question?
Yeah.
Yes, a softball question.
Okay.
Obviously, you've been talking about issues around certification and regulation and safety around this whole map architecture approach. It seems to me that a lot of what you said has applicability to the perhaps non-regulated health app world as well, and like with the Sharp Smart project and others. Could you just speak to that, not just smart, but also like maybe home health environments or mobile health environments?
Yeah, so the question is, to what extent could this be applied in other contexts that aren't necessarily safety critical? And the answer is, it's very applicable from a technology point of view, and it's more of an issue at the moment of dealing with political issues and the big players in the market who don't want to see any rigor added to their space. And they don't want to see any sort of enhanced regulatory scrutiny implied to consumer devices and that sort of thing. So, Paul, you could probably speak to this or confirm this, but there's a lot of sort of battling in the interoperability space right now, where some vendors want to push ahead with being able to have very lax regulatory scrutiny and standards applied. But something like this architecture, I mean, we've even done this. You can implement the ICE architecture on a phone, and use that to partition your apps on the phone. And you could do the same thing with your home, health network hub, and it would be very applicable there.
Comment?
Yeah.
Chuck Kilgore from the FAA. Two items. The FAA has an advisory circular 20-148 on reusable software components. And also, to Paul Miner's point about DO 297, the FAA also has an advisory circular 20-170 on integrated modular avionics development, verification, integration, and approval using RTCA/DO 297 and Technical Standard Order C-153.
Yeah, I think I've looked at some of those, but aren't some of those still, 10 years or so ago?
No, the last one I just quoted was October 2010.
Okay.
And the FAA is continually trying to update those, so they may be in the process, we may be in the process, we in the FAA may be in the process of updating those. The 20-148 is 10 years old, so it may have been updated, it may not have been. To my knowledge, it wasn't updated yet.
Sure. Can you send those numbers to John?
Yeah, that would be great. Thank you.